Hey everyone. Thanks for the introduction. I'm Dabby, a software developer at Shopify. But today I'm excited to talk to you about something that's not related to work, but more of a personal interest. I'll be talking about parsing natural languages. So first, a disclaimer. As you probably realize from the rest of this talk, I am not a linguist. And natural languages, they can be kind of difficult. So before we start talking about parsing natural languages, let's first take a look at some simpler kinds of languages, programming languages. So the great thing about programming languages is that they're non-ambiguous. So every line of code we write has one and only one parse tree that can be generated from it. And that's by design. So imagine a world where the Swift code we wrote got compiled differently at different times of the day. Well, that would be a disaster. So as a consequence of this characteristic of programming languages being non-ambiguous, and we can define a set of rules in a finite grammar, and then we can build a parser that's going to parse the code we write using these using the rules we write. So here's an excerpt of the grammar for Swift. So besides the rules defined in the grammar, no other external context is needed. So let's circle back to natural languages. So immediately that characteristic of non-ambiguity that I mentioned goes out the window. I'll try to drive my point with an example. So here's a very simple example. I bought a shirt with buttons. So let's walk through the parse for this. So first, you're going to have a noun-subject dependency from but to I. And next, a determiner dependency from shirt to And next, you have a case dependency from buttons to with. And then a nominal modifier dependency from shirt to buttons. And finally, an object dependency from but to shirt. So let's focus on this dependency that goes from shirt to buttons. Intuitively, we can see that this is the correct parse, as I, subject, but, verb, a shirt with buttons, noun phrase. Well, this isn't the only parse we can get from it. Let's take a look at another parse we can get. So in this parse, there's a dependency from but to buttons. And you can reason around this as buttons being a form of payment that I bought a shirt with. And here's another possible parse we can get. So notice now this dependency goes from I to buttons. And you can reason around this as buttons being a person who accompanied me to purchase a shirt. So to be precise, the total number of parses we can get for any given sentence is the Catalan number, that equation there, where n is the number of tokens in the sentence. So for a very simple example, you have a total of 132 dependency parses. But as we saw in the previous slides, though, only a handful of these parses would actually make enough sense to become ambiguous, and in which case we're going to rely on the context that we've built up since childhood to help disambiguate. So this makes defining rules for parsing natural languages very difficult, because this contextual knowledge has to be embedded into whatever rules we create in the grammar. So with every sentence we hear, our brain potentially has to select the most plausible parse from a bunch of possible parses in real time. So the rest of my talk is my best attempt to recreate how our brain behaves completely in Swift. So let's properly define our goal. So this is going to be our parsing pipeline. When given a sentence in the form of text, we'll first break the sentence down into appropriate tokens, and then the parser will output a dependency tree consisting of these tokens. So fortunately for us, Apple already provides a good enough tokenizer in their natural language framework, so we can just focus on the parsing aspect. So for a parser, we're going to be building a greedy transition-based parser, which when given an array of tokens will output a projective tree. So what are projective trees? For a tree to be projective, it must have no crossing dependencies. So if you look at the slides there, there's the bad and the good. So this is a slight simplification, unlike the whole problem of parsing natural languages. The reason for this being that natural languages vary with respect to the kinds of crossing dependencies that they permit. But the fixed word order of English generally allows for very few of these kinds of crossing dependencies. So this restriction should be fine, since we're going to be building our parser for English. So the initial state of our parser will comprise an empty stack, a buffer containing all the tokens in the sentence, and an accumulated parse that will start off as empty. At any given state, the parser has three options: a shift, a left, and a right. So let's see how each of these transitions will mutate the current state of the parser and the accumulated parse at the bottom right. Starting with a shift transition. So for a shift transition, we remove the first element in the buffer and push it onto the stack, like this. So a shift transition is valid if the buffer is not empty. Next, a left transition. The left transition sets the first element in the buffer as the parent of the topmost element in the stack. And we pop that element from the stack like this. And a left transition is valid if the stack and the buffer are non-empty. And finally, a right transition sets the penultimate element of the stack as the parent of the topmost element of the stack and pops that element from the stack like this. Yeah, I got animations because like this, explaining this is like kind of hard with words. Yeah, and a right transition is valid if the stack has at least 2 elements. Okay, so the parse is complete when the buffer is empty and there is only 1 token left in the stack, aka the root of the tree, at which point we'll return the accumulated parse at the bottom right. So let's go through a concrete example to see how these actions would in fact lead us to the correct parse. So back to our favorite sentence, I bought a shirt. Just a shorter version of this time. So the first step is to tokenize the sentences and add the tokens to the buffer. So for now, let's just hand wave and assume that there's this oracle that's going to tell the parser magically, here are the correct transitions you need to take at any given time that will lead you to the correct parse tree. And the oracle will usually suggest a shift, a left, or a right. And if it's a left or right transition, it would have a dependency label attached to it for labeled dependency parsing. So we start off with a shift transition. Oh, no. OK, so we start off with a shift transition to push I onto the stack. And then next is a left transition that sets bot as the parent of I with a noun subject dependency. And next, another shift transition. A shift again to push onto the stack. And then a left transition to set shirt as the parent of with a determiner dependency. And now a shift transition once more. And finally, a right transition that sets bot as the parent of shirt with the object dependency. So side note, I couldn't resist this pun. So when I say choosing the right transition, I actually mean choosing the correct transition, just so it doesn't confuse you. So I hope you can agree with me that having an oracle instructing the parser what transitions to perform at any given time is going to lead us to the correct parse at some point. So the problem boils down to just obtaining this oracle. So as I pointed out earlier with programming languages, every state of the parser must correspond to a handwritten rule in the grammar. So for a parser parsing programming languages, you just have to infer the next transition based on the rules that exist. So we've already established how arduous it's going to be to replicate this for a language like English. So we're going to be using an ML model for this. So now we have enough context about the problem. Let's now dive into how we'll create this ML model that will serve as our oracle from parsing, and in fact use it in an actual app. So the one restriction here is to do everything completely in Swift. So the first step is to train the model. To do this, we have to find data. So in order to train the model, we need to get a data set of dependency trees. And this data set consists of sentences and their corresponding parse trees. So in this domain, there are 2 popular data sets you find in most research papers. The first is the Penn Tree Bank, which is a curated data set of English that's released through the Linguistic Data Consortium, or LDC for short, while the other is the Universal Dependencies, which is an open source data set that spans over 70 languages. So one thing to keep in note here is that the parsing and labeling schemes are different depending on the data set you choose. So this is one criteria to consider when choosing a data set. So for me, the deciding factor was the Universal Dependencies data set was free and readily available for download. So this is an example of what the data set looks like for English. I've filtered out some of the columns to make things more legible. But you can see that each token in the data set has its parent specified by a token index, along with the relationship between the parent and the child. So the full format of the data set is available on your website. You can take a look if you're interested. So remember that we want our model to output the transition based on the current state of the parser. So we're going to go for an online training where we'll generate multiple examples from the data set and feed that to our model. So the architecture of our model is based directly off of the research paper above. It will be a neural network whose input layer will take in a set of features. The features are obtained from the current state of the parser and consist of words, their respective part-of-speech tags, and their dependency labels, if any. So these features are laid out in that order into a single vector, and they're passed into the next layer, the embedding layer. So the role of the embedding layer is to convert a word, tag, or label into a dense numeric vector representation. So it's basically a lookup table with a finite vocabulary size. So given a word or index of a word relative to that vocabulary, the layer returns, in our case, a 50-dimensional representation of the word. So there are pre-trained models available on the internet. In this case, I used the global vectors embedding, GLO for short, and augmented the vocabulary by adding all the lexical classes from the natural language framework, along with the possible dependency labels from the universal dependencies dataset. So our input vector gets sequenced through this embedding layer, and out comes a two-dimensional matrix, where each row is a 50-dimensional embedding of the word, tag, or label for that given row in the input vector. So this 2D matrix gets flattened in row major order in the flattened layer, and now it's back into a vector. And then the resulting vector gets sequenced into a custom hidden layer. Now this custom hidden layer comprises 3 weight matrices, where each of the weight matrices correspond to the 3 different feature types. So the input is split in such a way that all the word features are only sequenced through the weight matrix for words, and the same applies for the part-of-speech tags and the label features. So the resulting vectors from these 3 operations are added together, and the result is a single vector, and then we return this as the output of the layer. And finally, the last layer is the output layer and the output layer uses basically takes the output of the previous layer behind it as its input, and the result is a vector that's going to now represent the model's prediction, where each row is a vector corresponding to the likelihood of a given transition. So due to the complexity of this architecture, I think we can agree that we can't use Create ML, which is Apple's out-of-the-box machine learning creation software. So instead, we'll be using Swift for TensorFlow. So for those of you who don't already know about it, Swift for TensorFlow brings all the powers of TensorFlow as a machine learning tool to Swift. It adds first-class compiler and language support to machine learning. And one of this includes automatic differentiation, which is key when adjusting weights through backpropagation in a neural network. So let's walk through defining our model's architecture using Swift for TensorFlow. So here's our parser model architecture in Swift for TensorFlow. You can see the embedding, the flattened, the custom hidden layer, and the output layers as I showed in the previous slides. So the function, call is function, basically defines how the model composes the supplied input parameter through its layers. In our case, we basically want the output of the preceding layer to be the input into the next layer. So call as function also enables us to make predictions as like a syntactic sugar by calling into the model instance as you would a function, as shown above. And finally, as a plus, the core data structures of Swift for TensorFlow are codable. So this enables us to save and retrieve our model during and after training. So this is our training code from a very, very high level. The parser trainer basically encapsulates the logic behind generating the transition examples and also adjusting the weights of the model during training. Now, when the training is done, the parser trainer is going to save the version of our model that had the best accuracy on the validation set, and it will save this as JSON using a JSON encoder. So after training, it's always good practice to test the model on data it hasn't seen before. So we do this by retrieving the best model from our parser trainer and then evaluating on the test data. So the results are approximately 75% labeled attachment score accuracy, which is the LAS, and 80% unlabeled attachment score accuracy. So the labeled attachment score is an accuracy metric which checks how many of the dependencies, along with your dependency labels, that the model predicted correctly. While the unlabeled attachment score, as the name implies, doesn't take the dependency labels into account. So at this point, the model training is complete. We now have a saved Swift for TensorFlow model, and now we want to convert it into an ML model. So first, let's take a look at what exists out there. So Apple provides core ML tools for converting from popular machine learning models like Keras and scikit-learn into an ML model. And there is also TF Core ML, a converter for converting from a TensorFlow graph into an ML model. So unfortunately, we can't take advantage of this here because to the best of my knowledge, there's no way to convert a Swift for TensorFlow to produce a TensorFlow graph from a Swift for TensorFlow model. So we'll have to build our own converter that will take our Swift for TensorFlow model and convert it into an ML model. So before we can start implementing our converter, we need to know what comprises an ML model. So an MLModel is basically a binary file serialized in Google's protocol buffers format, or protobuf for short. The full protobuf specifications for defining an ML model are available in the Core ML tools repository. You can take a look if you're interested. So as a prerequisite, we need a way to use these Core ML specifications in our project to convert our model into Core ML. Enter Swift for protobuf. So Swift for protobuf is an open source library maintained by Apple. It generates Swift code from protobuf specifications defined in .proto files. It's very easy to use. You can just install it via Homebrew and run the protalk command specifying that a Swift output be generated. Now, once you've generated these files, you can copy them into your project. But in order to use them, you need to use the Swift protobuf runtime library that's also available in that repository. And you can pull this in through Swift Package Manager. So now we can use the generated code we have to convert our model. So again, here's our converter code from a very high level. We basically start with an empty Core ML specification and build it up to match our model's architecture. So the generated classes always have the Core ML specification prefix. So here, we create an empty Core ML model and set the specification version to 4, which means it should use Core ML 3. Yeah, I know, it's weird. But new in Core ML 3, models can now be updated in real time. So after they've been deployed, basically on the user devices, we can update the model as the user interacts with it. But to keep things simple, we're not going to use this in our model. So we'll set is updatable to false. So next, we specify that the Core ML model is a neural network composed of a neural network specification that we create in the make neural network function. And we then return the built ML model serialized as bytes. So for time reasons, I won't be able to dive any deeper into this conversion code, but I'll have a GitHub repository at the end. So now we have our converter, and we can now use it to convert our trained Swift for TensorFlow model into an ML model and save it to file. In our case, we're saving it to the downloads directory. So after converting the model, it's always good practice, again, to test that the converted model, that the accuracy of the converted model doesn't vary by a very suspicious amount. So in our case, after conversion, there was a drop of about 0.01%, which is kind of expected because of floating point arithmetic. So now we have an ML model. Let's now see how we can use this in an app. So we'll be embedding our ML model into an app that will help us visualize the parse tree of a given sentence. So the UI part of the app has been completed, and all that's left is the last step. And we basically want to embed our ML model so we can start producing the correct parse trees so we can visualize them. So the first step is to add the ML model to the app. And this is as simple as a drag and drop. Now, once the model gets added to the project, a Swift class gets automatically generated for the model, along with its input and output data types. So finally, let's walk through the code for parsing our model. So first, we create our parser state. And this basically encapsulates the empty stack, the buffer filled with all the tokens from the sentence, and an accumulated parse tree that starts off as empty. So while we're not in the terminal state, we're going to do the following. We first fetch all the valid transitions that can be performed in that state. And next, we ask the model to predict the likelihood of the transitions based on the current state of the parser. And then we're going to pick the valid transition with the highest probability. And this will either be a shift left or right. And if it's a left or right transition, for label dependency parsing, it will have the dependency label. So we apply the best transition on the state, and we basically repeat this until the state reaches the terminal state, at which point we return the resulting parse tree. So there's been a lot of code shown on the slides, but there's an old saying that a demo is worth 1,000 slides. So let's take a look at the app. Okay. Nothing. 1 second. Slight technical difficulties. Still nothing? OK, there you go. OK, so I'm going to start with a very simple sentence that I'm sure all of you are thinking. I hope this goes well. OK. So looking at this, we can kind of look at the parse, and you can see that it's going to be correct. So usually, whoops. Usually, let's just ignore that. So usually, the verb is going to be the root of the whole sentence. And here you can see there's the noun subject, I hope something, which is going to be the rest of the sentence, and hope what? That this goes well, with the sentence terminator. So let's try a more complicated one. So at least I think so. OK, so this one is also kind of complicated. But walking through it, you can see that there's two separate sentences with the conjunction and. So if you look at the first sentence, the root is going to be giving. So I'm giving my first talk. And then there's the conjunction relationship between the two verbs of the sentence, so from giving to going. And then if you look at the second sentence, the root of that part is going. And then it's going great with the sentence terminator. So finally, let's look at the last parse that you've all been waiting for. I bought a shirt with buttons. So unfortunately, at 75%, our model still thinks buttons is a form of currency. So nothing much we can do there. Let's just switch back to the slides. Oh, OK. OK. So to summarize what we just saw, this was basically an attempt to replicate how the brain parses natural languages. And we're able to do so with about 75% accuracy. But the main point I wanted to focus on is that we're able to do all of this completely in Swift. We basically started from a natural language processing research paper to an app that validates the proposed solution. So how awesome is that? That's pretty awesome, if you ask me. So there are still some kinks here and there, but I'm really excited for what the future holds with machine learning becoming a native functionality in Swift. I truly believe it will help create greater apps and help encourage more people to jump into the domain of machine learning. So here's the link to the GitHub repository and also the demo. Thanks so much for listening. I'll be at the question booth if you have questions.